Okay, so the question we're going to try and answer today is what is the distribution of first passage times of a random walker? So let me just define that question a bit better. So let's say we have a random walker in a single spatial dimension, okay? And so I'll draw it like this. So let's say this is time along the horizontal and space along the vertical. And we start at some position x naught, and our random walker is going to take a bunch of random steps, and at some point the random walker is going to touch the origin. Okay, that's x equals 0. At this point, some amount of time has passed, and we can call this amount of time capital T. And the question that we want to ask is, what is the distribution of T? So T is a random variable, right? Because every time we do this experiment, we'll get a different value of T. And we want to know what is the probability distribution of T. And T, you'll hear some people will call it the first passage time. So it's the first time that the random walker touches the origin. So how are we going to go about solving this problem? So we can define some probability density function of T, which is in the end the thing that we want to solve for. So it's going to be a probability density of T, but it's also going to depend on the initial position, because you can imagine that if I start really close to the origin, then the distribution of first passage times is going to be concentrated at smaller values, and if I start really far from the origin, it's going to be concentrated at larger values. And so there's this dependence on x naught. And what we can do is come up with a kind of recursion relation for this probability distribution that we get by conditioning on the first step of the random walker. So let's say that that first step is some delta x, which has some probability distribution. So I have delta x, and it has some probability distribution, and we'll come back later to what this distribution might be. But for now, we can say for any arbitrary distribution of this delta x, how could we get a kind of recursion relation for the probability distribution of first passage times by conditioning on the initial step. So imagine that we took an initial step delta x. Well, there would be some probability of taking that initial step. And if we had taken that step, now what would we need in order to get a first passage time of capital T? Well, let's say that that initial step had taken some amount of time delta t. So it's taken some delta x in some amount of time delta t. Well, now what we need in order to get the same capital T as our first passage time is we would need, after getting this initial delta x, we would need to have a first passage time of t minus delta t. But now we wouldn't be starting from x naught, we would be starting from x naught plus delta x. Okay, and now what we have to do is we have to integrate over this whole thing with respect to delta x, because delta x can be any number of things. For each of them, it'll give a contribution to this probability of having capital T as your first passage time. But you have to integrate over all these possibilities. So this is kind of the important relationship, which is like a recursion relation for this first passage time distribution. So how can we turn this into a more usable form? Well, what we're going to want to do is we're going to want to Taylor expand this term in brackets. So if I Taylor expand this for small delta t and small delta x, what I'll get is p of t comma x naught minus delta t times the derivative with respect to capital T of p, and then plus delta x derivative with respect to x naught of p. And then I'm going to keep a second order term for reasons that will become clear, delta x squared, and the second derivative with respect to x naught of p. Okay, so now this is the expression I have, and we want to see whether we can do this integral for a particular distribution of delta x. So what is the integral that we need to do? You see that we have p of delta x, and then we have p of t, x naught, minus delta t derivative plus delta x dx naught plus delta x squared over 2 dx naught squared. Okay, so first I can ask, what is the distribution of delta x? And for this, we're going to assume that our random walker is kind of continuous time random walker that satisfies the stochastic differential equation. So it's just some kind of Brownian noise satisfying the stochastic differential equation. X dot equals psi of t, where psi is delta correlated noise. So that psi of t prime is 2d times delta of t minus t prime, where d is some kind of diffusion constant. So what this means is that the distribution of delta x is just a Gaussian with variance 2dt, right? So, sorry, 2d delta t. So I'll have 4 pi d delta t, and then minus delta x squared over 4d delta t, right? So this is just my Gaussian with mean 0 and sigma squared 2d delta t. Okay, so now this makes it easy to compute this integral. So you'll notice that we're integrating over delta x. These terms don't depend on delta x. This term also doesn't depend on delta x, and neither does this term. So really the only things that we have to evaluate are the expectation of delta x and the expectation of delta x squared. And these we know how to do because we just specified the distribution. So what do I get? Well, I get that the distribution, the expectation of delta x is just 0, right? Because it's a symmetric Gaussian. And delta x squared, the expectation of this, well, this is just going to be sigma squared or 2d delta t. Okay, and so now you see why I kept the second order term, because if I just kept a first order term, it would vanish. So I want to keep the leading order term. Okay, so now having done this, what we have is that this expression is equal to, so you'll see that, so the terms that don't depend on delta x, when we integrate over delta x, we'll just get a factor of 1 multiplied by these, right? Because this p of delta x is normalized. So what we end up getting is p minus delta t dt p plus 0 times dxp, so I won't write that, and then plus d delta t dx naught squared p. Okay, and our original statement was that this is actually equal to p itself. So this is kind of what we've gotten by doing our Taylor expansion, and you'll see that we can simplify this, right? So we have, if we simplify this, we have that the time derivative with respect to this first passage time is equal to d times the second derivative with respect to the initial condition of the probability distribution. And so this looks a lot like the diffusion equation you might recognize. But the interpretation is a little bit different because here t is the first passage time and x naught is the initial condition. So how can we go ahead and try to solve this? So we're going to solve it by Laplace transform, which is something you may have seen from how you solve the diffusion equation, but things are slightly different because of the way in which we specify initial conditions. So the Laplace transform of p with respect to t, this first passage time, is going to be the following. So s is the conjugate variable to t, and so the Laplace transform is defined as the integral from 0 to infinity of p of t x naught e to the minus st, and we integrate over t. So what this means is that the inverse Laplace transform of p hat, which is going to give us back p, will be the following, and we'll use this form later, but I'll just write it down for now. So the inverse Laplace transform is going to be 1 over 2 pi I integral from gamma minus I infinity to gamma plus I infinity of p of s x naught e to the st integral over s. So in this case, gamma is just some number that's chosen in order that, oh sorry, this should be p hat. So gamma is just some number that's chosen in order that p hat is convergent along the contour that we integrate. And so it can be actually any number of things. But we'll see more about this when we have to invert our Laplace transform. But what this means is that this partial differential equation can be rewritten as an ordinary differential equation in terms of p hat. So what we get is that s p hat equals d times the second derivative with respect to x naught of p hat. Okay, and this is, you'll see there's only a x naught derivative here, so this is an ordinary differential equation, and we know how to solve this. So what do we get? We get p hat of s comma x naught is some coefficient a times e to the minus square root of s over d x naught plus b e to the positive square root of s over d x naught. And a and b are coefficients that we don't know, but we can figure them out based on the initial conditions. So what are the initial conditions? So if you remember the picture of the random walker where we started at x naught, we did something, and then we ended somewhere, some amount of time t later, we ended at the origin. Well, so if I start at x naught equals 0, then I know that my probability distribution of the first passage time is just a delta function. In other words, I will always have first passage time 0. So what this means is that p of t comma x naught equals 0 is delta of t. Okay, and because we know how to Laplace transform a delta function, this means that p of s comma x naught equals 0 is 1. Okay, and that will help us figure out what a and b are. So it turns out we're going to set b to 0 because this thing blows up for large x. So on physical grounds, we don't think that's a realistic term to have. And then this fact that p of s comma x naught equals 1 is equal to 1 allows us to say that a has to be 1. So now we have our p hat. So p hat is simply e to the minus square root of s over d x naught. Okay, so we're almost there. We just need to inverse Laplace transform this now. And so if I write that into our formula for the inverse Laplace transform, what I get is that p of t comma x naught, which is the function that we wanted to begin with, is going to be 1 over 2 pi I integral over this contour of the exponential of minus s over d x naught plus st. Okay, and we integrate over s, sorry. Okay, so how do we evaluate this integral? So if I draw a picture of what we're trying to do in the complex plane, so this is the real part of s, and this is the imaginary part of s. Well, we want to do our integral over some contour that looks like this, right? Where it's offset from the imaginary axis by amount gamma, and we want to go from negative imaginary infinity to positive imaginary infinity. We're going to want to close this contour and then use the residue theorem to evaluate what the contribution from this leg of the contour must be. So imagine that we have some infinite contour that goes up to infinity and then comes around like this, and then closes at negative infinity. Well, we know that since our function has no singularities within this region, um, that total integral over the closed contour must vanish. And so what this means is that the contribution from the bit that we're interested in has to exactly cancel with the contribution from this arc that we've added. However, there's a bit of a complication, namely the function that we're trying to invert, which is here, this e to the minus square root of s, that's multi-valued. And so how do we understand that? Well, we know that when you take a square root, in general, there can be two answers, a positive and a negative root. And the same is true for complex numbers. And this means that if we try and integrate some function that depends on a square root over the complex plane, there's a bit of ambiguity in how we choose this. So how do we get around this? Well, we're going to want to define our function to be single valued. So how do we do that? Well, let's say that if this is the complex plane, then if I have any number in the upper half plane with positive imaginary part, then when I take the square root, I am going to, let's say I have some angle theta here, and say that the radius is r, so I have r e to the I theta. If I take the square root of this, I'm going to define it to be square root of r e to the I theta over 2. And if I have something in the lower half plane, say some number here, where this angle here is theta, then I define the square root of this, which is square root of r e to the minus I theta. I define this to be square root of r times e to the minus I theta over 2. And you'll see that this makes our function single valued. This makes the square root function single valued because it eliminates the second root. So if I wanted to take the square root of this number, well, I could have something that's here in the complex plane, or I could have something that's opposite, that's somewhere over here. But with my current definition, I define that this must be the square root, and similarly for things in the lower half plane. So this introduces what's known as a branch cut along the negative real axis, where the definition of the function is discontinuous. And so what we need to do when we evaluate our Laplace transform is we can't just naively close the contour as I've drawn in this picture. We have to close it in a way that avoids this branch cut. So this is what's called a Bromwich contour. So what's it going to look like? Well, here's the bit that we're actually interested in, right? This bit that's going to give us the answer to our inverse Laplace transform. But when we close it, so there's a branch cut right along the negative real axis. And so we need to avoid this whole section so that our function is unambiguously defined everywhere. So when we close it, we're going to skirt this. We're then going to make a little loop around the origin, and then we're going to go back the other way. And we're going to close it at minus imaginary infinity. So this is the Bromwich contour, and now our task is to evaluate this integral, right, which is 1 over 2 pi I, the exponential of all this stuff, which I wrote up above. We want to evaluate this integral over the contour. And in particular, we know that the integral will vanish over the contour because there are no singularities inside. And so we know that if we can figure out what are the bits, what are the contributions from this part that I've just outlined, they must exactly cancel out the contributions from the part that we're interested in. And so we can get at the part that we're interested in by doing this other integral, which will turn out to be easier. So that's the next thing that we have to do. Okay, so how do we evaluate this integral over the contour that we've drawn here? And remember, we're going to focus now on the parts of the contour that close this vertical line here, because we know that they must be equal and opposite to the contribution from the vertical line. So there's this contour, there's this segments out here at kind of infinite radius, and it turns out that these vanish. And the way you could see that is if you parameterized s by some r, capital R, e to the I theta, and you took r to be something very large, and you looked at the magnitude of the integrand, you'd see that it actually vanishes as r gets very large. And I'm not going to do that out fully here, but that's a good thing to just check. And so what this means is that those aren't going to contribute anything. Now, similarly, we have this little bit around the origin here, like a circle around the origin in the clockwise direction. And that circle we can make vanishingly small by saying, along this circle, s equals epsilon e to the I theta. And then we take epsilon to 0. Epsilon goes to 0. So in that limit also, this contribution from the circle around the origin won't contribute anything. And that's something else that you should check. But you should be able to see that relatively straightforwardly. And so then the bits that we need to worry about are this thing coming from negative infinity to 0, and then from 0 going back to negative infinity. And these things are going to be different precisely because there's a branch cut at along the real axis. And so the definition of our square root function is discontinuous above and below the real axis. So how are we going to write this? So what we're going to have is that p of t comma x naught is going to be the negative, right? Because it's equal and opposite to the bits from this this contour that closes the vertical contour. So it's going to be negative of, so we have something coming in from negative infinity to 0. And what's that going to be? So it's going to be the exponential of, so we have our square root function, but now we're above the real axis. And so that means that the square root of s, when it's some negative number above the real axis, is going to just be is. So we have exponential of negative I times the square root of absolute value of s over d, x naught plus st ds. And then we have the contribution where we go from 0 back out to negative infinity. So that's going to be integral, so plus integral from 0 back out to negative infinity of exponential. But now you have to remember that the definition of our square root function is different. So we said that for numbers in the lower half plane, we're going to define the square root function. So if there's a number that's e to the minus I theta, well, the square root of this is e to the minus I theta over 2. And so this means that instead of positive I square root of absolute value of s being the correct root, we're going to take the negative root. So the sign of this term is going to be opposite. Okay, so that's the importance of the branch cut, and everything else is the same. Okay, and close this parentheses. So we now need to evaluate this integral, and what you can already see probably. So we can switch the bounds on the integrand, and we can switch the bounds on the integral, and we can write this as a single integral, which is just, we'll keep the negative sign outside, and we'll take the integral from negative infinity to 0 of I square root absolute value of s over d and then we'll have to put a minus sign here because we switched the bounds. S naught plus st. Okay, and ds. And what you see if you simplify this or factor out the e to the st is that this is exactly equal to 1 over pi times integral from 0 to infinity. So I've again made a substitution of u equals minus s, but I'll just call it s, and I get sine square root s over d x naught e to the minus st ds. Okay, So this is exactly what P of t comma x naught is. And so we need to evaluate this integral. So how are we going to do this? Well, it's going to be convenient to write this the sine function as the imaginary part of a complex exponential. So this is going to then be 1 over pi integral from 0 to infinity of the imaginary bit of e to the e to the I square root s over d x naught minus st ds. Okay, and here I won't go through all the steps, but I will say, so if you make the substitution u equals square root of s, you get an integral on which you can complete the square, and that allows you to then solve it just as a Gaussian integral. Once we do this, and we take the imaginary part, the answer that we get is x naught over 2 square root pi d e to the minus x naught squared over 4 dt over t to the 3 halves. And this is our final answer. So what does this mean? Well, the important thing that we wanted to know is what is the dependence of this probability distribution on big T, right? So for a given x naught, if I give you an x naught, this allows me to tell you what the shape of the distribution of first passage times is. And you'll note that for large T, this decays as t to the minus 3 halves for large T. And so it decays as a power law, not as an exponential. So it decays rather slowly. And in fact, the really pretty amazing thing, I think, is that this means that the mean of this distribution, so if I wanted to calculate the expected value of the first passage time, which would be the integral of P of t for some given x naught times t dt, this actually diverges. And you can try and do that, because if you can see that, because if you just look at the big T behavior and you put in t to the minus 3 halves here, you'll be integrating t to the minus 1 half, and that gives you a square root of t evaluated from 0 to infinity, and that diverges. So the amazing thing is that the mean is divergent, and that's kind of the intuition behind that, is because your random walker can wander off really far before it comes in and hits the origin. And so what we've seen through constructing a partial differential equation and solving it by Laplace transforms is this really rather counterintuitive result, which is that although we can be sure that our random walker will hit the origin at some point, the mean time at which it hits the origin is actually divergent.